Section 4.3, Exponential Functions. So first off, before we get into the exponential functions, let's remind ourselves of our exponent rules. So all of the letters that we're about to use are going to be real numbers. A has to be greater than 0 and B has to be greater than 0. If that's true, if you have two of the matching bases, a raised to the s times a raised to the t, that's multiplication of matching bases, which means that you add the exponents. If you have a power raised to a power, that is a raised to the s raised to the t power, that's multiplication, so s times t. If you have a power on a set of products, that power goes to each factor in the product, so a to the s power times b to the s power. 1 raised to the s power is always going to be 1, no matter what s is. A raised to the negative s power, well, that's going to be 1 over a to the positive s power, or you could also write that as 1 over a all raised to the positive s power. And then if we have something raised to the 0 power, that's going to equal 1. So, an exponential function is a function of the following form. Now, specifically right now, I have the letter a. But when we're working with exponential functions, a is going to be a number. It may be 2, it may be 7, it may be the number e. But watch out, a will be a number, and then x is going to be the variable. Now, specifically, a can't be 1 because otherwise it's not very interesting, because 1 raised to any power will always be 1. But a will be positive for us. Otherwise, it gets kind of weird. So some common characteristics of this exponential function is that it's continuous and it's one-to-one. Remember that continuous just means there's no jumps, gaps, breaks, or holes, and no sharp corners, cusps, anything like that. One-to-one, now we know, means it's going to pass not only the vertical line test because it's a function, but it will also pass a horizontal line test. If we ever allow a to be a number less than 1, but greater than 0, because that was already required, so a fraction, then what actually is going to happen is it's going to be a decreasing function instead of an increasing function. And if a is going to be a number greater than 1, then it's an increasing function. And it's going to be increasing or decreasing based on a for its entire domain, so just watch out for what a is. A less than 1, decreasing function. A greater than 1, increasing function. The domain is going to be all real numbers. The range, unchanged, if we don't do any transformations or translations to a to the x, is going to be from 0 to infinity, where 0 is not included. Now, specifically what actually happens is that there is a horizontal asymptote at 0. And it will have the y-intercept 0, 1. Now that's going to be because if you plugged in the value 0 for x, anything raised to the 0 power is going to give you 1. So what does the graph of this exponential function look like when a is greater than 1? Well, specifically, it's going to look like this. Now, this is the general trend. For this one, I'm letting the base be 2. And so for this exponential function of the base being 2, it looks like this. It has a general trend. Specifically, it's going to go through the value 1a, where in this situation a is 2. And so, but this is the trend. Notice that because a is greater than 1, this thing is an increasing function on this entire domain. Recall that there is a horizontal asymptote on this y equals 0, and we just have this nice shape. This is what an exponential function looks like. Now, if we change that and we let our a be some value less than 1, in this situation we're letting a be a half, notice that this is a decreasing function instead of an increasing function. Otherwise, everything really looks the same, and remember that point I said 1a is still there. Because if you plug in 1 here, 1/2 raised to the first power is 1/2, and so you get the value 1 1/2. You also get the ordered pair 0, 1 that showed up earlier, and notice that you now have a decreasing function. And we also have this horizontal asymptote at y equals 0. Now, if we're trying to graph these things, then we're going to use the same transformations that we had before. That is, stuff inside the function affects horizontal stuff, stuff outside the function affects vertical stuff. But if we just want to adjust this specifically to our exponential function, it looks like this, where the inside the function stuff is the stuff that's in the exponent. And so if you have any stuff with the exponent, that's going to be horizontal things, and anything outside is going to be vertical. So specifically, if a is negative, what's going to happen is it's going to turn the function upside down. It reflects the graph over the x-axis. If a is a number bigger than 1, in absolute value we just ignore the sign, then it's a vertical stretch by a factor of a. If a is a number between 0 and 1, then it's going to be a vertical compression, or shrink, vertically by a factor of a. B is going to affect horizontal stuff because it's inside, so it's up here. And if B is negative, it's going to reflect the graph over the y-axis. That is, it's going to turn sideways. If B is bigger than 1, then it's going to be a horizontal compression. If b is a number between 0 and 1, it's going to be a horizontal stretch. Then c is just going to shift this left or right depending, so watch out. If this is x plus c, then it's going to shift it left. Remember, inside is backwards. If c is a negative number, then it's going to shift it that amount right. Then d, being on the outside of the function, outside, is a vertical translation, and so if d is positive, it shifts the whole function up d units, and if it's negative, then it shifts the entire graph down d units. Now for an example of these transformations. Notice that we do have an exponential function. Now I'm going to go ahead and rearrange this to make it look like the way we've dealt with all our other transformation function problems. And so this could be rewritten as 2 raised to the x minus 3 power minus 4. The first thing that I want to consider is, what is my parent function? My parent function is 2 to the x, which is just the exponential function with a base of 2. Let's notice that there are two things that are changing what this function looks like. Specifically, this minus 3 here is inside the function. Since this minus 3 is inside the function, that's a horizontal shift. They're backwards. Minus 3 makes it go right 3. Then notice that I have this minus 4, which is outside the function. And since it's outside the function, it's going to do vertical stuff. So minus 4 is actually going to go down 4. Since we have these transformations, if we wanted, we really could sketch this graph pretty quickly. And so let's remind ourselves, what does 2 to the x look like? Well, 2 to the x looks like this. More or less, that's what the function looks like if we put it on an xy coordinate plane. Well then, if I want to know what does 2 to the x minus 3 minus 4 look like, this thing is a function where we move right 3 and down 4. Well, remember that there's actually a horizontal asymptote at 0 for that original function 2 to the x, which means that we now have a new horizontal asymptote at y equals negative 4 because we moved down 4. Then we've also moved this point here to the right 3 units. So 1, 2, 3. And so it's going to be about right there. Then I know that this function more or less will look like this. Recall that the domain for all exponential functions is all real numbers. It doesn't matter what transformations we do to an exponential function. As long as we don't put in some sort of square root or division by a variable, our domain is going to remain all real numbers. But the range could change. Now, up here, when we talk about the range for this parent function that I have up here, the range for it is really from 0, not including, up to infinity. Now that's because of that horizontal asymptote at 0, we know that this exponential function will not cross that. But here we've moved that down 4. So what's happened is just the y value that we start at is shifted down. And so now it's shifted down to negative 4, and then it continues up forever, up to infinity. And because we've now shifted this horizontal asymptote in our picture, our horizontal asymptote is now at y is equal to negative 4 because that's how much of a vertical shift we had. In general, if you're trying to find the horizontal asymptote, all you need to consider is, did it shift up or down any? Your shift is going to give you your horizontal asymptote. And if this is an exponential function in this form, the range will come directly from once you know the horizontal asymptote. Now we have 4 times 1/2 raised to the negative x. All right, so first off, let's think about our parent function. Well, our parent function is 1/2 raised to the x power. What does that look like? Remember that that's a decreasing function with a horizontal asymptote at y equals 0, so that looks like this. Then what happens? Well, we have two things occurring. We have this, and we have this. Well, this 4 is actually going to be a vertical stretch. So it's a vertical stretch of 4. That is, it's going to quadruple in height. Well, what else do we have? We also have this negative here. Well, this negative is inside the function, and so that's a horizontal reflection. And a horizontal reflection is specifically a reflection that flips it sideways or across the y-axis. And so it's going to turn it sideways, and then it's going to stretch it vertically. But those are the only transformations that we have. You remember that the domain is going to be, again, all real numbers. Nothing changes there. The range, because we had no movements up or down, the range remains the same as the parent function because there's no upside down reflections or reflections across the x-axis, so our range is going to go from 0 to positive infinity. And because there was no shifts up or down, the horizontal asymptote is still going to be y equals 0. Now if you wanted me to sketch this real quick, what is this going to look like? Well, because there's no up-down shift, this function will actually flip horizontally, and so this thing will just spin on its axis to give us our new one, and that's going to look like this. Now the problem is I probably didn't stretch it as much as I could or should, but because I haven't written any scale on here, I say that's good enough. That's all that's happening. It's a vertical stretch that is reflected across the y-axis. Some exponential functions that we're going to deal with are going to have a base e. The number e is a famous irrational number like pi. E is an interesting thing, and it's really difficult to explain without actually having some calculus to understand where it comes from. But it comes from calculus. And it's an irrational number like pi, that is, it's a non-terminating, non-repeating decimal. And if you were to write out some of the digits, it's going to look like this. E is approximately 2.71828182, so on and so forth. Non-terminating, non-repeating, which is why we write it as the letter E, because we don't have another way to write it. It's going to follow the same rules as exponential functions of a base a. Now realize that because e is larger than a, we know the exponential functions with base e will be increasing functions. So here, if we want to describe the transformations for f of x is equal to 2 times e to the x plus 3, and then determine its domain, range, and horizontal asymptote, nothing is new or interesting here. E is a number greater than 1. Since e is greater than 1, we can say, oh, well, I know this function is increasing. Well, if I were to graph the parent function e to the x, it just looks like this. It has a horizontal asymptote at y equals 0. That's the unchanged version. But notice that we have two things occurring. Specifically, this moves it up 3. This is a vertical stretch of 2. And that's it. That's everything we have going on. Now to talk about the domain. The domain, just like all other exponential functions, is going to be all real numbers. Anything we want to plug into this exponential function works. Well, the range and the horizontal asymptote, maybe it's easier to talk about the horizontal asymptote first. And where is the new horizontal asymptote? Since the horizontal asymptote has to be shifted up 3, I know that it moves from y equals 0 to y equals positive 3. We just have to consider our vertical shift when we're looking for the horizontal asymptote for exponentials. Well, then, once we know that the horizontal asymptote is at y equals 3, and then this is a vertical stretch, if we wanted, we could sketch this real quick. And so, given an xy coordinate plane, I know that now I'm just shifting up this horizontal asymptote to 3. Then my exponential function is just a vertical stretch, and it looks something like this. Well, then our range is going to be specifically everything from positive 3 up to infinity. Now watch out for vertical reflections. If we ever reflect vertically, then it's going to turn this upside down before you do a shift, and so it will change the range being below the asymptote instead of above. But that's all the information we needed. We're good. To solve exponential equations, we should do our best to write each side with a common base. So for these, if I have 2 to the 3x is equal to 4, I just need to write 4 with a base of 2. But 4 is really 2 squared, and so that is 2 to the 3x is the same thing as 2 squared. Well, at this point, because the bases are the same, now you can set the exponents equal to each other. So that is 3x is equal to 2. Then we just solve for x the same way we would before. Divide by 3, divide by 3, x is equal to 2/3. Let's try it again. Over here I have 8 raised to the negative x plus 30 power is equal to 128. For this one, I think we should write 8 as a base raised to some power and also try to write 128 as a base to a power. Now what I'm thinking is 8 is the same thing as 2 cubed, and so that is 2 cubed raised to the negative x plus 30 power. 128 is the same thing as 2 to the 7th power, and so I can rewrite 128 as 2 to the 7th, all raised to the x power. Then I need to get the bases to match perfectly, so I need to deal with some exponent rules to help this out. But a power to a power is multiplication, and so this is then going to be 2 raised to the negative 3x plus 90 power is equal to 2 to the 7 times x power. Then we have matching bases. The exponents are the only thing that's changed up here, so 2 raised to this power has to be equal to 2 raised to that power, so that's negative 3x plus 90 is equal to 7x. So then we just solve. I'm going to add 3x add 3x, 90 is equal to 10x, divide by 10, divide by 10. I get that x is now equal to 9. Once again, we just want to try to get everything to have a matching base. And so I see that 5 and 25 both have a base of 5. That is, 25 is equal to 5 squared, so I'm going to rewrite that as 5 squared raised to the x power times 5 raised to the x squared power is equal to, well, 625, is that 5 raised to some power? Yes, 625 is 5 to the 4th. So that's 5 raised to the 4th power all squared. Well, then we use our exponent rules. So powers to powers of products, that is 5 squared to the x power, 5 raised to the 2x power, and then 5x squared, that one's already there. So that's 5x squared. And then 5 to the 4th quantity squared, that's going to be 5 raised to the 4 times 2, or 5 to the 8th. Then I have multiplication of matching bases, so you add the exponents. That's going to be 5 raised to the 2x plus x squared is equal to 5 to the 8th. Then I have matching bases, and I can just set the exponents equal to each other. That's going to be 2x plus x squared is equal to 8. Now I have a quadratic, so pick your favorite method of solving after I put everything on one side. This is then x squared plus 2x minus 8 is equal to 0. I'm going to factor this because I think that's the easiest. Two numbers that multiply to give us negative 8 but sum to be positive 2. They are x plus 4 times x minus 2. Then via the zero product property, that's going to give me x plus 4 is equal to 0. X minus 2 is equal to 0. I get that x is equal to negative 4 and positive 2. Those are my solutions. Next, we see that we have 2/3 raised to the x power. And I see that I have another fraction over here, 16 and 81. But I really just want to see if there's any way I can write 16 and 81 as some prime base raised to a power. And so 16 is 2 to the 4th. And 81 is 3 to the 4th. So this is 2/3 raised to the x power is equal to 2 to the 4th power divided by 3 to the 4th power. But using exponent rules, that's the same thing as saying 2/3 raised to the x is equal to the power over the quotient can pull out and make this 2/3 raised to the 4th power. And at this point, notice that I have matching bases 2/3 and 2/3, and so that is x is equal to 4. And we're done. Let's do it again. I have 2 raised to the x squared minus 3. Can 4 be written as 2 raised to some power? Yes, it can. So this is then going to be 2 raised to the x squared minus 3 power is equal to 2 squared raised to the x power. That's going to be 2 raised to the x squared minus 3 is equal to 2 to the 2x. Then we have matching bases, so I can set the exponents equal. That's x squared minus 3 is equal to 2x. I see that I have a quadratic. That is x squared minus 2x minus 3 is equal to 0. Then if I can factor this, I'm good. And this factors as x minus 3 times x plus 1 is equal to 0. Then I get that x is equal to positive 3 and negative 1. Those are our solutions. For the next one, notice that our base is going to be e. So this might seem a little strange, but we just need to get everything into a single base e on each side. So I have e to the negative x squared on the left, and I have e to the x quantity squared times 1 over e to the third. So I need to have matching bases just e. So this is e to the negative x squared is equal to e to the x quantity squared is e to the 2x. Then, if I want to get e cubed to have something that I can multiply times e to the 2x, that is e to the negative third, using power rules, then I have a product here, e to the 2x times e to the negative third, that's addition. So then I get e to the negative x squared is equal to e to the 2x plus negative 3, or minus 3, which then I have matching bases. So this is negative x squared is equal to 2x minus 3. Now I have a quadratic again, and I can solve this. I'm going to move the negative x squared over, and that's going to give me x squared plus 2x minus 3. I see that this will factor as well. this factors as x plus 3 times x minus 1. Negative 1 times 3 is negative 3. Negative 1 plus 3 is positive 2, and x times x is x squared. So I get that x is equal to negative 3 and positive 1. Now for an example using exponential functions. So the price P in dollars of Mrs. Armstrong's Jeep Grand Cherokee that is X years old is modeled by P of X is equal to 38,465 times 0.92 raised to the X power. Now specifically, this function takes in years and outputs value. Notice that because 0.92 is a number less than 1, you can think of this as a depreciation problem. That is, the value will decrease over time. So if we want to know how much our car should be worth when it's 3 years old, we just need to evaluate P of 3. That is 38,465 times 0.92 raised to the third power. Then we just have a calculator value that's going to be 38,465 times 0.778688, which I'm actually going to round to 2 decimal places since we're talking about money. And so that means that it should have a value in 3 years of $29,952.23. And that's my approximation. Then what is it going to be worth in 9 years? Same thing. P of 9, that's going to be 38,465 times 0.92 raised to the 9th power. I get that this is approximately 38,465 times 0.4722, rounding that number. Then finish with rounding to 2 decimal places. That times 38,465. I get 18,161.69 cents. Once again, I have chosen to round it to 2 decimal places because I know that it's money that we're talking about, and usually we think about it in terms of pennies, unless you're at the gas pump. And so let's go back to the meaning of 0.92, and remember that since 0.92 is less than 1, what we're actually saying is the car is decreasing in value as time moves on. That is, it's a depreciation. And so really this base 0.92 is some depreciation factor, or how quickly it will lose its value. So now let's look at another function. Let's say that d of h being equal to 5 times e to the negative 0.4 times h can be used to find the number of milligrams d of some certain drug that is in a patient's bloodstream h hours after the drug has been administered. And so if we want to know how many milligrams will be present after 1 hour, this calculation is just plug the value into the function. D of 1 is equal to 5 times e raised is 5e raised to the negative 0.4 times 1. Well, at this point, it's just a calculator value. You can find that e button on your calculator. I get that the approximate value of this e to the negative 0.4 power is approximately 0.67032. And watch out for your rounding. You may need to round more or less depending upon requests. But then I discover that this finished rounding is there's 3.3516 approximately milligrams that will be present after 1 hour. Now if we want to know how many milligrams will be present after 6 hours, same idea. We're just going to plug in that value 6 into the function and see what we get. That's going to be 5 times e to the negative 0.4 times 6. And so that is 5 times e to the negative 2.4. So then I'm going to use that e button on my calculator, the natural number e. E raised to the negative 2.4, I get that this is 5 times 0.090718 approximately. Then multiply that times 5, and I get that this is approximately 0.454. So then let's round this to 4 decimal places just like we did the previous. So that's going to give me 0.4536.